Okay, so our third speaker this morning is Silvio Giancola. He's a research scientist here at KAUST, working under the supervision of Professor Bernard Ganem in the Image and Video Understanding Laboratory, part of the Visual Computing Center and the Artificial Intelligence Initiative. In 2022, he founded Thea Technology, a KAUST startup that enables AI for everyone through a no-code simulation online platform that delivers AI-based computer vision as a service through the generation of custom image detection models. So, thank you very much.
Thank you for the introduction. All right. Good morning, everyone. My name is Silvio Giancola, and today I'm going to talk about harnessing the power of computer vision for energy-related applications. Thank you for the kind introductions. I'm going to repeat myself, but basically I'm a research scientist at KAUST, working under the supervision of Professor Bernard Ganem, and I'm affiliated with the Image and Video Understanding Laboratory, part of the Visual Computing Center and the Artificial Intelligence Initiative. And as you mentioned, I also founded a company called Thea Technology that tried to enable AI for everyone. So part of our work in terms of research is actually in the Image and Video Understanding Laboratory, and we focus on three main areas. That goes from video understanding, vision for automations, and the fundamentals theory that leads to the latest generation of computer vision algorithms based on deep learning. Today, I'm not going to focus on all the research we are doing, but I'm actually focusing on one particular aspect, one of the products I've been working on that's called cloud labeling. But first, because not anyone here is actually familiar with what computer vision is, I would like to give you an introduction of what I meant by computer vision. I won't be technical at all, but will just give you like some generic highlights. When we talk about computer vision, usually we talk about, I talk about not generative tasks like the GANs and so on and so forth, but more the discriminative task. How can I understand what's inside the images in order to give insightful information to my system? Those algorithms are typically object classification or image classification, like understand that in the right, on the left side, we actually have a cat. The task of localization, which is localizing, for instance, with bounding boxes, where is the specific object in an image. Object detections, which actually tackle multiple objects detection and localization. And instance segmentation, try to identify each single pixel, what are the boundaries of those objects. But there's also many other tasks, but now I would like to focus on those discriminative tasks. Computer vision is mostly artificial intelligence. Artificial intelligence applied on visual data. In fact, we are using typically deep neural networks that basically, in that specific case, for instance, classify whether we have an image of a cat or a dog. And interestingly enough, actually the results are nowadays on par or even superior than human for those specific tasks. So if I need to bounce back on the comment on the previous presentation, yes, sometimes AI is more intelligent than human, because humans sometimes are tired, make some mistakes, and are currently in some specific task. If we really narrow the task into some very specific things to do, we can actually perform better than what a human can actually do. But artificial intelligence, the reason why it actually worked well is because of the availability of data. In fact, AI exists for the last 50 years. It's one subfield of artificial intelligence is machine learning, the fact of learning from the data. And deep learning is one of the reasons why it actually have boomed and performed some very good performances, as in the presentation that we have seen before. Oh, technical issues? Okay, all good. So from this availability of the data, what I'm more interested in is like the visual type of data. So data that come from cameras. Okay, I'll try that again. Technical issues. Here we go. So now we have like a large amount of data available nowadays, which come from security cameras or satellite images, or even on a phone, we actually have like cameras everywhere. So visual data is now ubiquitous. But you also need like some nice compute power, and this is also like one of the perks of being here at KAUST. We actually have access of really good supercomputers that allow to train and to learn from this data in order to then deploy those algorithms and run inference on those data. But what are the type of application we can actually do in energy-related topics? One of the examples, for instance, of computer vision could be like analog control recognition, trying to understand what different sensors or what different visual information can actually shown to you or to any worker in some factory. Can also focus on, for instance, the analysis of switches to understand if something has been disconnected or not. Also trying to focus on personal protective equipment that basically identify whether someone is following all the rules of the security. But computer vision has some limitations. In fact, usually it requires large enough data sets. By large enough, we never know how much data is actually needed. One of the previous questions was, can we actually get better results with more data? I would say yes, but at some point you actually saturate. But you need large enough data set in order to achieve good performances. Another limitation is that you don't just need the data, you need annotated data. And this annotation can be extremely time-consuming. You need to draw bounding box around objects to identify which car is in which lines, for instance. And the last limitation is actually okay, not working. Okay, is basically it requires large amounts of GPUs. So GPU is really what have enabled the power of deep learning for computer vision. That we can have a lot of chance here at KAUST to have access to a large amount of GPUs. But how to cope with those limitations if you don't have access to all of that? Big tech companies already have the know-how. They already have the data, the annotations, and they all also have enough resources in order to train their algorithms. But small and medium-sized companies still struggle in that things. But also small labs or some researcher like us actually might struggle into developing deep learning algorithms for their own task. So how can we deliver computer vision to a broader audience? And then really the question is like, how can you harness the power of computer vision right now? The solution for that is cloud labeling. Basically, cloud labeling is one of the projects that we have been pushing forward for the last 3 to 4 years that is currently available through the platform THEA Technology. What is cloud labeling? So cloud labeling is, too much slides. Cloud labeling basically provides computer vision as a service. Computer vision as a service, basically it's a platform where you can upload, annotate, train, and serve algorithms. It's a no-code platform, does not require a single code to use that platform, and it provides you with state-of-the-art computer vision algorithms. And on top of that, we are leveraging several techniques such as active learning to put still the human in that loop in order to provide the best performances and still have control on those performances. I will give you an example now with one of the projects that I was working on early 2019, which has nothing to do related to energy, but it's actually illustrates very well the example of how can we harness the power of computer vision. Some of those scientists actually have a lot of microscope images. In particular, it's actually seeds. Nothing's particularly interesting maybe for this crowd, but they have hundreds and hundreds of those seeds. They were using cloud labeling as a way to automatically provide insight and scale up their analysis to a large amount of data. And with cloud labeling, they were able to actually have 2 outputs, which is data that are annotated, that could be useful for any field, but also a trained model that is available for you to serve online in order to use it right at the power of your hand. So how does that work? Cloud labeling, basically, all you have to do is upload a batch of images, such as this one. Then you annotate your images with a bounding box in that specific case. You can either manually annotate them, you can upload those annotations if you already have generated somehow, or you can even run inference on the previous model that you've done before. Then you can just, like with one button, train a model for your custom data that will serve for your custom needs. And then you can reiterate until satisfactory results are actually obtained. So either this would correspond to a large amount of annotations for your experiments, or also a model that has enough performances for your needs. The outputs are 2. One of them is just a data set that is fully annotated. That could be very useful for your personal use. Maybe you have a large-scale data that you need to annotate. And it's using active learning for fast annotation. So active learning is one technology that learns from your unlabeled set of data which data is necessary to annotate in order to provide more information to your model. Second type of output is an AI algorithms, in particular for computer vision, that is deployed on the cloud, which is basically served for remote inference, and then you can actually harness the power of that specific models anywhere in the world as soon as you have an internet connection, which means, yes, your phone. And you can have full access to your models using the typical library using computer vision and deep learning, which has PyTorch, and in this particular case, MM detection. So in summary, cloud labeling allow you to annotate some images that you can label such that you can train an algorithm automatically and infer the results on more images through that models. And it leverages several technologies that I won't enter too much into the technical details, which are transfer learning, the fact of learning from a large-scale data sets of generic images that has been customized then for your needs. Active learning, which is the concept of selecting which images are more informative for your models to annotate next. And online learning, the fact of continually annotating eventually from the model that you have trained and simply focusing on correcting the mistakes of your algorithms. Let's talk a little bit about how cloud labeling can actually enhance your applications. And I will show you a few examples of how cloud labeling has been used in the last 2-3 years. And I will focus on one particular one that is related to energy. So one of the first projects I was mentioning to you is basically this automatic assessment of seed germinations. It might not be very useful for you, but there are some plant scientists that create like hundreds and hundreds of those microscope images on a daily basis. They have a lot of students that actually count how many objects there is in specific microscope images, and it takes them like 50% of the time. With our platform, they were able to save 99% of the time by automatically generating those analysis of those experiments. Another example is a collaboration with the Ministry of Culture that goes another completely different field, which is not microscope images, but up to satellite images, where we're looking for unreferenced archaeological sites. So we're able to scan the whole, we collaborated with the Ministry of Culture and some archaeologists here at KAUST, and with a data set of 1,000 archaeological sites that were already referenced, we managed to train an algorithms that recognize those sites on satellite images, and we're able to scan the whole kingdom of Saudi Arabia in only 150 GPU hours, which means that with the power that you actually have here at KAUST, takes you less than 10 minutes. So it actually led to some really nice discovery, and of course it can also be applied to any other type of application from satellite images. I let you to your imagination for any of this application. Another application that we developed. Okay. Another application that we've developed that actually won the Falling Wall Berlin Science Week in 2020 here at KAUST is the automatic assessment of overfishing in the Red Sea. So we developed a proof of concept where we were able to to count how many fish and recognize which type of fish has been fished in fisheries. So that was basically tested in, it was just a proof of concept, so it has not been fully tested, but at least the algorithms were here to provide a full proof of concept to test the technology. And the last application that I wanted to mention is a collaboration with neuroscientists that basically were interested in the localizing and identifying neural spine detections. Those are actually neurons. And it's actually funny to understand that neural networks are actually looking at neurons. It's kind of like looking at yourself in a mirror. So from all those applications, we basically either automated some analysis, accelerate some analysis, provide some insightful insight, and all those models were trained on cloud labeling, and it only takes really a fraction of the time that you could actually take for you to hire an AI engineer, annotate the data, train the data. It typically takes like weeks or months. You can actually have those models in a day or so. But let's focus on one of the last applications I wanted to mention is about energy, right? Because the title is AI for energy. So one of the applications that we were running for the last 2 years was a collaboration with Aramco, where we're trying to read those analog gauges. It's something that many factories have in the world. They are not necessarily sensorized, and currently, how people do the sensing is that they just go from one gauge to another and take what's the reading that's actually showing. What we're trying to do is the following: automate that part. How can we take an analog gauge, take some pictures from a tablet, and run some image processing, machine learning approach that will basically read that value for you, such that the person, the worker in that factory, only have to go from gauge to gauge and just take picture of that, and will automatically read and synchronize that on a remote servers and digitalize somehow this reading. So really the main goal for that project was to develop a mobile application that can automatically and reliably read gauges at Aramco facilities by just taking a picture. So how did we work for that? You remember one of the issues of, one of the limitation of computer vision and deep learning in general is that you need data, you need annotations for this data, and you need GPUs. So GPUs, we have that. Data, we don't necessarily have that, and annotation even less. How can we cope for that? We actually leverage what we call sim for real, using simulated data to train a neural network that basically will work then in the real world. There is a lot of engineering trick in that part, but it actually works. So here what you can see is actually some renderings of fake gouges that has been more or less realistically modeled. So you can see like some of them have some reflection. We have modeled like some reflection of the glass, for instance, some dirt as well. But the nice thing is that from those simulated data, you can actually have annotation for free because you already know where the needle is, what's the range, and so on and so forth. So taking this data, how can we train a neural network? How can we train something that will then work also in the field? One of our solution was, first of all, run semantic segmentation, which is one of the tasks I was presenting on my very first slides, that consists in classifying every single pixels into a specific semantic. And here we were understanding what's the background, what's the center of that gouge, and where's the needle of that gouge. So for that, we use like a typical segmentation network based on different architecture. And we're able to get those very clean semantic segmentation mask. Then, using this information again, we actually trained a classification network that was able to classify to regress the needle angle, the start angles, and the end angles for this specific gouge. So it works quite well. This is what one of the tests that we actually did in the laboratory here at Aramco. Actually, one thing that I wanted to mention here, I forgot to mention, is actually that by leveraging this intermediate representation, that is basically just the mask itself, you kind of make abstraction of the image itself, because that's now the input of the classification network. So if you are able to get that mask, this is the new input for the classification network. So it means that if you are able somehow to have a segmentation network that provides you a good segmentation mask out of that image, you can actually get some very good transfer capability. And this concept goes towards the name of modularity. So learning modular neural networks that can then transfer well. So these are some of the first examples that we tested in a controlled environment. We're able to do semantic segmentation of the needles, and we were able to actually get the exact reading of 27, which is actually shown here. Of course, sometimes there are some errors. Here, for instance, we have an error of a few percent. The actual numbers, the actual reading should have been 7. It's actually 6, which is just a 1% error when you see the range of that gouge. But then we tried that also on the field, and it does look completely different. Although, thanks to the modularity of that approach, we were able to read the values of those gouges, although they are extremely difficult to read due to light reflect, to shade, to shadow, to dirt. It's really impressive, the results that actually managed to perform. So in conclusion, cloud labeling is able to, and what we're doing in our lab, we are able to deliver computer vision based on deep learning to a broader audience. If you use cloud labeling, you don't necessarily require to know how to code, so it's a no-coding platform. We are using active annotation with a human in the loop, so the human is still like in control of what's happening. And we are doing two things, model serving, so remote cloud inferences. So we're serving these models on the cloud for you to access it from your phone through communication or whatever device has access to internet, but also edge deployment. In the example I showed you in the tablet, actually the model was deployed in the device, in a local on-device inference. And with that, I conclude my talk. I leave the rooms for some questions if you'd like. Feel free to scan this QR code and have a nice overview of what the THEA technology and with the technology of cloud labeling can do for you. Thank you.
Okay, got time for a couple of questions. Okay, over there.
Hi, thank you. That was a really interesting talk. I was wondering if you've benchmarked your cloud labeling platform against some of the free open access computer vision things like the one that pops into my head is Google's Teachable Machine. Like, how does it perform compared to those open access models?
You mean like a Google Cloud Platform, for instance, the different tools that are available in those cloud platforms, right?
Well, there's a plug-and-play one called Teachable Machine that runs off of TensorFlow.
Okay. Cool.
And so I was wondering if you'd considered benchmarking.
I've benchmarked with like some other technologies. So I'm more referring like to the algorithms that are actually running. I don't know which one they're actually using in that one. But one of the findings of cloud labeling is that most of the advances that we have seen in computer vision in terms of designing what's the best algorithms in terms of architecture, should we use CNN, should we use transformers, actually there is still one key hypothesis, which is I have enough data. And if you have enough data, which is order of millions, maybe billions, you can see like one model being better than the other. But actually what is the most important part is having this data. And at low regime, this ranking of which algorithm is actually better is not necessarily the one you can actually see when you have a lot of data. So actually here the key technology that is implemented and that actually make cloud labeling strong enough is not necessarily the algorithms that we are using, although we are fairly competitive with the latest state of the art because this is like the research that goes directly from our labs to the platform. So right now, I have deadline in like 24 hours for 5 other papers with my students. So that to give like the pace of what we are doing. But basically, the key idea is active learning is actually what accelerates the annotation process and really try to identify if you have a small. People can actually have a lot of data, but they are unstructured. They need like some labeling. If you identify which data to label, you can reduce by a factor of 3 or 4 the amount of annotation that you need to fulfill some specific task and reach similar performances. So the key technology, I would say, in here is being more data efficient and reduce the annotation burden. I hope that answers your question.
Absolutely. Thank you so much. It was really informative.
Yeah.
Well, thank you. One more question.
Thank you, very nice talk. A couple of quick questions. The edge deployment, I think that's quite powerful. But for image processing, I would imagine you need some special chip. You can't just use the inherent chip there. Yeah. And the second is that on the satellite imaging, as you said, there are numerous applications. One comes to my mind is detecting emissions, right? Like gas leaks or natural gas leaks. Not sure if you have looked at that.
Yeah. Thank you for those 2 questions. So the first question was about deployment. Yes, you need like some specific devices. Although nowadays, like some models actually run on your phone, you don't necessarily have specific you don't need like an iPhone 14 Pro to actually run those models. I would say if you want to do edge detections and you want to have something that is real time, which means that faster than 30 frames per second, because typically camera provides you 1 frame every 33 milliseconds, 30 frames per second, you will need like some specific devices. Those specific devices are typically the NVIDIA Jetson, which is kind of like a small Raspberry Pi computer that has some GPU capabilities, more called CUDA cores, which are basically the compute power that enable faster inference through efficient CNN type of operation that can run on those specific hardware. But some models actually run just a bit slower. So if you don't have real-time restriction, you can actually run that on a Raspberry Pi with a specific hardware. It just takes, instead of like a fraction of a second, it will take maybe 4 or 5 seconds to run. That's for the first questions. Yes, edge deployment might require some specific devices if you have real-time requirement. For satellite images, I have not tried yet the emission, but one of the challenges in satellite images is that every specific application or field actually have specific type of is leveraging specific type of data. Typically, if you take Landsat type of satellite images, you actually have multiple wavelengths that, or with the bandwidth that basically, wavelengths that basically focus on specific type of data. And one of the example, if you want to localize like the vegetation, for instance, there is a vegetation index, which is a linear combination of multiple wavelengths. So I guess there is a specific combination of wavelengths that could be very interesting for emissions from satellite images. Having that knowledge allows us to create images with that, which has a specific visual meanings for you that allow you to understand where the different emissions are. Typically, the rule of thumb for computer vision is that since the performance are on par with human, if you can do it with your own eyes, typically, the AI can do it as well. But it can't, it's not magical, I would say.
Okay, with that, let's thank our speaker. Thank you.
I can take that.